Today we'll learn how do you know if an object's in free fall, how to set up a problem for an object's thrown upwards versus being dropped, and how do you know which equation to select to solve the problem. Let's get started. So first let's start out by talking about what is free fall motion. This is when an object is either thrown up in the air or it's falling down. The object's vertical acceleration is always going to be due to gravity. So AY is going to be equal to negative g, or negative 9.8 meters per second squared. The other thing to consider, we usually define free fall motion as an object that is only experiencing the force of gravity. And the other thing to consider with free fall motion is usually there's only 1D or one dimension of motion. So oftentimes that is vertical, it's just falling, moving up or down, and there's no horizontal motion. In order to learn more about a 2D perspective, that's going to be looking at free fall. In order to look at a 2D perspective of motion, that's going to be projectile motion, which is my next video, which I will link somewhere up above. But first, let's learn the basics. So an object being dropped is the most straightforward version of free fall. So as you can see in our diagram, we have a tennis ball that is going to be dropped and it is falling downwards. The first thing is that when an object is being dropped, its initial velocity is going to be zero unless we're stated otherwise, right? We're always going to assume it's zero, and this is because it's located at the maximum height. We also know because the object is in free fall, the acceleration is going to be due to gravity, that negative 9.8. The last thing is, because our object is falling downwards, you can see that I have our Vy final is going to be a negative number. Because we start out with our initial velocity being zero and we have a negative acceleration, that means that our velocity is going to get more negative over time, causing the object to speed up until it hits the ground. Let's look at the example of an object being thrown up. In fact, it looks similar, but if you flip the picture, right? Initially, if an object's being thrown up, that means that it's going to have a velocity that is not zero. So you should be given an initial velocity or you may solve for it. In this case, because it's moving upwards, we know that that initial velocity is going to be positive. Again, it wouldn't be free fall motion without our acceleration being due to gravity. So our AY is still going to be negative 9.8 meters per second squared. And the key thing that's a little bit different is that since the object's initial velocity is positive and our acceleration is negative, the object is going to slow down until it reaches its maximum height. At the maximum height, we know that its velocity is going to be zero because after it reaches its maximum height, it's going to start to fall down. And that means in order to change from a positive velocity to a negative velocity, it's going to pass through zero. The last thing is we want to recall those kinematic equations that we've been working with because we're really going to start to use them to solve some equations and they apply to freefall motion as well. If you haven't learned about this, I recommend checking out a video that I do specifically on how to pick the equation to use. But as a quick refresher, just know that each of the equations are able to solve for different components of the object's motion over time. Let's go ahead and try an example together. First, let's look at a dropped object example. A coin is dropped from a fountain 4 meters above the base of the fountain. Okay, so first thing I want to do is go ahead and label my position. So our initial position is 4 meters, and our final position is approximately 0, right? It's about 0. Then we're told what is the final velocity of the coin right before it hits the bottom. So again, our height is basically 0. However, it's right before it hits the ground. That way the object still has velocity. Yeah, it's still moving. And the other thing that we can fill in is we know that our coin is being dropped, so our initial velocity should be 0. And we also know that it's in free fall, therefore it is accelerating due to gravity, which is going to be negative 9.8 meters per second squared. Now that we have everything we need and we're told to ignore air resistance, which is perfect. If there was air resistance, there could potentially be a change in our acceleration. We have position and displacement, we have our initial velocity, and we have acceleration. We don't have time. The key thing here is don't have time. Because we don't have time, yes, you could solve for it using the displacement and time equation, but honestly, we can do it using a different way. We do have displacement and velocity, and there's an equation that uses those two. And that equation is going to be Vy final squared is equal to Vy initial squared plus 2 times Ay times delta y. Now again, if you don't do all the subscripts, that's perfectly fine. I'm just using the y value in my subscript to represent the fact that it's moving vertically. Feel free to use the x direction and the x notation, especially if that's what your teacher has you doing. In this case here, I know that I want to solve for Vy final, so this is already perfectly set up for me. I'm going to go ahead and plug in the numbers that I do know. And that's going to be Vy initial squared, which is just 0 meters per second squared, plus 2 times negative 9.8 meters per second squared times our delta y. And remember that displacement is equal to the difference in our two positions. So it's y final minus y initial, or you could say to yourself, what direction is it moving? It's moving down, which is a negative direction. Therefore, your displacement should be negative 4 meters. Now that we have this, our last step to do is to calculate. You can see that our negatives will cancel, and so it's really important that you don't forget that gravity and displacement are negative in this problem. So in this case here, we would go ahead and grab a calculator. Vy final squared is equal to 78.4 meters squared per second squared. And then our final step is going to be to square root both sides to solve for just Vy final. So Vy final is equal to the square root of that number. And once again, we put that in our calculator and we get 8.85 meters per second. Now, last thing, are we done? Hopefully you're saying, wait, you forgot something. And we did. Velocity is a vector. And because our coin is falling down, this value needs to be negative. So make sure that you don't forget that negative in front of your solution. And we did it. Okay, let's look at one more example. But instead of having the object fall down, let's have the object move up first. So in this case, we have a diver jumps up with an initial velocity of 24 meters per second on a diving board. Okay, ideas, initial velocity up, diving board located 15 meters above the top of the pool. Okay. What is the total time that it takes for the diver to reach the top of the pool? Ignore air resistance. Okay, so thoughts. The first thing that I know is that this distance right here, from the top of the diving board to the top of the pool, is going to be 15 meters. And then we have an initial velocity. So they're originally jumping up with an initial velocity, Ui naught is equal to positive 24 meters per second. Again, they're still being affected by the acceleration due to gravity. So our acceleration is still downwards. Okay, and we're trying to figure out what is the total time that it takes for the diver to reach the top of the pool. Now, here's the thing that we have to consider. We know that the diving board is located 15 meters above the top of the pool. But the issue is that they're not it's not just a time for the person to travel 15 meters because they're going to move up in the air first and then they're going to come back down. So what we need to figure out is how long does it take for them to reach the maximum height, which we know their velocity at the maximum height should be 0 meters per second. So I'm kind of thinking of this in two pieces. We have the person that's traveling on their way up. Let's switch colors to label this clearly. Okay, so we have T1, which is kind of the person reaching their maximum height, and that's going to be part of the time. And then we're also going to have that journey coming back down from the maximum height till they reach the top of the pool is a second time component. We're going to take those two times and add them together to get our total. Okay, so let's begin with the first part. So in order for us to solve for the first piece, we need to figure out how long does it take for the diver to reach their maximum height where we know their initial velocity at the top is 0. So first I'm going to solve for T1. And in this case, I have the initial velocity, the final velocity, and the acceleration. Therefore, the equation I want to pick is the equation that uses velocity and time, which is going to be Vy final equals Vy initial plus Ay times T. In this case, I'm going to now substitute in my equation that I have here and the variables that I've set up. So in this case, my Vy final is going to be my Vy max. Vy initial is our actual initial velocity. In this case, Ay is the acceleration due to gravity, and the T that we're specifically solving for is T1. So I'm going to make sure that I label it so I keep track of what I'm solving for. In this case, I'm going to go ahead and plug in my numbers. I got 0 is equal to positive 24 meters per second, because remember they're initially moving up, plus negative 9.8 meters per second squared times T1. And we want to solve for time. So in this case here, I can see I'm going to start out by putting the velocities together. So I'm going to subtract 24 on both sides. That's going to leave me with negative 24 meters per second is equal to negative 9.8 meters per second squared times T1. My last step, right now T1 is being multiplied by acceleration. So to get it alone, I'm going to divide on both sides. And we can see here, this is really important. Those negatives will cancel, and so we'll be left with positive time. Time is a scalar value. Therefore, our time should always be positive. If you are getting a negative time, something is wrong in your calculation or in your setup. So make sure that you double check your equation and the numbers that you're using. Check the signs of everything to see if there's an error there. Okay, at this point though, we're going to grab a calculator to solve for T1. And our units should be seconds. Okay, so when we divide negative 24 by negative 9.8, we get 2.45 seconds, approximately. Okay, but we haven't finished the problem. We still need to solve for the time that it takes for them to reach the top of the pool from the maximum height. So that's going to be our second step. So now for T2, our Vy max is now our initial. Our V final, we don't know. So here's the thing. This value down here is not given to us. So we don't have that to work with in this case. We do have the initial velocity and we do have acceleration. However, we technically have some displacement, but not the whole thing. We're kind of in a pickle. There's a couple ways to approach this. I think that the best way to go moving forward, though, is to go ahead and use the time T1 to determine how much vertical displacement was created by the diver in that first time period. And so, because if we know that, then we can know the total displacement and we can use that to solve for T2. So what I'm going to say is the first step is to solve for delta y1. So again, we're solving for the vertical displacement that took place during that first segment of motion. In that case here, I'm going to want to go ahead and use the equation for, in this case, I'm going to want to go ahead and use the equation for displacement and time because I'm trying to solve for how much farther the diver traveled up. That way I know how long it'll take them to make that full path to the top of the pool. So in this case, I'm going to have my Vy initial times T1 plus 1/2 AY T1 squared. Okay, so in this case, I'm solving for delta y. It's already set up for us. I'm going to have 24 meters per second times 2.45 seconds plus 1/2 times negative 9.8 meters per second squared times 2.45 seconds squared. And once again, we're going to grab calculator to get that displacement there. And our solution is 29.39 meters. Right? So that's going to be our total height moving upwards during that time. So to get our total displacement, right, for T2, that's going to be equal to the initial displacement, which was 15 meters, plus how much higher the diver went. So we're just going to add those two together, 15 meters plus 29.39 meters. And that will give us our total displacement on their way back down. So in this case here, we're going to go ahead and add them together. We're going to be left with 44.39 meters. So that's the maximum height that the diver is going to fall. Now that we have our total displacement, we can go ahead and calculate T2 because we have our initial velocity, we have our displacement, and we want to solve for time. And I'm going to use that same equation again because we have displacement and we have initial velocity and we have acceleration. So I think it's the best equation to use. So step 2, now we can go ahead and solve for T2 using our total vertical displacement. So in this case here, let's plug it in. Let's set it up. First things, delta y2 is going to be equal to our initial velocity. In this case is our diver at their maximum height. And so because they're at their maximum height, that's going to be the Vy max in this case, times T2 plus 1/2 AY T2 squared. Now, here's the thing. Because our initial velocity when the diver is at their maximum height, because we're measuring the time from the max height to the top of the pool. In this case, that term is 0, which I love. Anytime something goes to 0, it's awesome because that means that our equation is actually a lot nicer. It's delta y2 is equal to 1/2 AY T2 squared. That's what we're working with. So we know what this one is. We have 44.39 meters is equal to 1/2 times negative 9.8 meters per second squared times T2 squared. Okay, so first step, I'm going to simplify the right-hand side. And that will give me negative 4.9 meters per second squared times T2 squared. Okay, now I just caught myself in something. And maybe you were looking at me and saying, what is she doing? The thing is, I am not even following my own suggestions. In this case, when we solved for the maximum height, that was 44.39 meters, right? But here's the thing. If we're talking about what delta y2 actually is, it's the diver going down, which means my displacement is going to be negative. So I need to make sure that this is negative. Again, how did I catch myself in this mistake? I caught it because when I was looking, if I were to divide that positive displacement by the negative acceleration, if I try to take the square root of that, I get an imaginary number or a complex solution. And we don't want an imaginary time. It should always be real. So in this case here, that made me like, uh-oh, something needs to be negative. Those negatives need to cancel. So again, sometimes we forget to make the displacement negative, a velocity negative, or acceleration negative. Because we have so many terms that are vectors in these kinematics equations, it's really important that we're thinking about the directions all the time. So now I can go ahead and I know I'll get a real solution. I'm going to divide both sides by negative 4.9. And I'm going to grab that calculator one more time. So I'm going to go ahead and divide to get an answer of 9.06 seconds squared is equal to T2 squared. Again, I'm just rounding most of these numbers, but our final step is going to be to square root. And our final answer is going to be that T2 is approximately equal to 3 seconds. Again, my solution was like 3.009, but approximately 3 seconds. I hope that this is helpful for you because I would say these are one of the more complex questions that you may run into where you need to strategize and figure out how you're going to get to the ultimate solution. We now have the time that it takes for the diver to go from the diving board when they travel up in the air to their maximum height. That's T1. Then we went ahead and we used that T1 information to solve for the vertical displacement upwards, right? That was initially positive. But then we said, okay, well then measuring the displacement from the diver's maximum height to the top of the pool is going to be the height of the diving board plus the height of the diver in the air. And that's how we got our delta y2. We then took that, plugged it into our displacement written time equation to then solve for T2. And now we have everything that we need to get the final solution, which is going to be the total time, right? So our total time is going to be the sum of those two components. And so in this case, T total is equal to 2.45 plus 3 seconds. So that's going to be 5.45 seconds. Thank you so much for sticking through that problem with me. I know that it was a lot of work, but I hope that being able to talk through some of the common errors and things that you'll run into together will help you have a better idea of how to approach these free fall problems. As always, I am so grateful that you are here, and please remember that your growth will be found in the journey rather than in the solution. So get out there and go practice some physics problems, and I will see you in the next video.